Hi friends, today we'll see how to minimize deterministic finite state machine. If we are going to solve a real problem with an FSM, we may want to find the smallest one that does the job. We'll say that a DFSM M is minimal if and only if there is no other DFSM M dash such that L of M is equals to L of M dash and M dash has fewer states than M. We might want to be able to ask first, given a language L, is there a minimal DFSM that accepts L? Second, if there is a minimal machine, is it unique? Third, given a DFSM M that accepts some language L, can we tell whether M is minimal? And fourth, given a DFSM M, can we construct a minimal equivalent DFSM M dash? And for all these questions, the answer is yes. And in this lecture, we will concentrate on answering the fourth question, that is, given a DFSM M, can we construct a minimal equivalent DFSM M dash? Suppose we have a DFSM M that accepts L. Possibly M is the only definition of L. In this case, we must construct a minimal DFSM to accept L by starting with M rather than with its equivalent L. There are two approaches to construct a minimization algorithm. First one is to begin with M and collapse redundant states, getting rid of one at a time until the resulting machine is minimal. Second approach is begin by overclustering the states of L into just two groups, accepting and non-accepting. Then iteratively split these groups apart until all the distinctions that L requires have been made. Both approaches work, but we will be using the second approach. Our goal is to end up with minimal machine in which all equivalent states of M have been collapsed. So in order to do that, we need to understand what do you mean by equivalent states and thus collapsible. Two states Q and P in M are equivalent, which we will write in the form Q is equivalent to P if and only if for all strings W belongs to summation star, either W drives M to an accepting state from both Q and P, or it drives M to a rejecting state from both Q and P. In other words, no matter what continuation string comes next, M behaves identical from both states. Note that this sign is an equivalent relation over states. So, it will partition the states of M into a set of equivalent classes. MinDFSM is the algorithm used to minimize the given DFSM. Let us have a quick look on the MinDFSM algorithm. Initially, we will be having two classes of states, one accepting states and the other rejecting states. In the second step, we are supposed to repeat until a pass at which no change to the classes has been made. So initially new classes is equals to null. At each pass, we build a new set of classes, splitting the old ones as necessary. Then this new set becomes the old set and the process is repeated. For each equivalent class E in classes, if E contains more than one state, see if it needs to be split. For each state Q in E, look at each state and build a table of what it does. Then the tables for all states in the class can be compared to see if there are any differences that force. Then, for each character C in summation, determine which element of classes Q goes to if C is red. If there are any two states Q and P such that there is any character C such that when C is red, P goes to one element of the classes and Q goes to another, then P and Q must be split. Create as many new equivalent classes as are necessary so that no state remains in the same class with a state whose behavior differs from it. Insert these classes into new classes. If there are no states whose behavior differs, no splitting is necessary. Insert E into the new class. At this step, classes is equals to new classes. The states of the minimal machine will correspond exactly to the elements of the classes at this point. We use the square bracket notation for the elements of classes that contains the original state Q. Return M dash is equals to classes summation delta in the square bracket start state of M, and Q, the elements of Q are in AM, where delta M is constructed as if delta M of Q comma C is equals to P, then delta of M dash is equals to in the square bracket Q comma C is equals to in the square bracket P. No class that contains a single state can be split. So, if length of K is K, then maximum number of times that MinDFSM can split the classes is K minus 1. Since MinDFSM holds when no more splitting can occur, the maximum number of times it can go through the loop is K minus 1. Thus, MinDFSM must halt in a finite number of steps. M dash is a minimal DFSM that is equivalent to M since M dash is minimal. It splits classes and thus creates new states only when necessary to simulate M. And L of M dash is equals to L of M. The proof of this is straightforward by induction on the length of the input string. Let us see how to minimize a given FSM. This DFSM is over summation 01. We'll see the operations of MinDFSM algorithm at each step. Initially, we'll be having two classes, one class consisting of accepting states, another consisting of non-accepting or rejecting states. In this DFSM, we have two states E and F as accepting and rest all A, B, C and D as rejecting or non-accepting states. Initially, we have two classes A, B, C, D and E, F. In step 1, we are supposed to check if any class has more than two states, then is it possible to split them further? Here, in both the cases, we have more than one state. So, let us check one by one, starting with EF pair. From each state to each input symbol, check it is going to which class, that is E0, E1, F0, F1 going to EF class or ABCD class. First, E0 is taking a self loop to E. E is in EF class, so E0 goes to EF class. E1 taking a self loop, so E1 goes to EF class. Similarly, F0 and F1 are taking a self loop to state F. F is in EF class, so F0 and F1 both are going to EF class. On checking the pattern, we see that there is no change in the pattern. That is, E0, F0 are going to F, E1, F1 are going to F. So there is no change in the pattern. It means state E and state F are indistinguishable from each other. So no splitting required. Similarly, let us check for ABCD class. A0 is going to state C. C is in ABCD class. A1 is going to state B. B is in ABCD class. B0 is going to state E. E is in EF class. B1 is going to D. D is in ABCD class. C0 is going to F. F is in EF class. C1 is going to D. D is in ABCD class. D0 is going to state E. E is in EF class. D1 is going to state F. F is in EF class. Now, if we observe the pattern, there is change in the pattern. That is, A0 and B0 are going to ABCD class, which is not similar with other states. D0, D1 is going to EF class, whereas B and C states are in the same pattern. That is, B0, C0 is going to EF, B1 and C1 are going to ABCD. So it means B and C are indistinguishable from each other. So there are three different patterns obtained. So we must split these into three classes: A, B, C and D. So by the end of step 1, we come across 4 states: A, B, C, D and EF. So in step 2, we have to check whether BC and EF can further be split. B0 is going to state E. E is in EF class. B1 is going to D. D is in class D. C0 is going to F. F is in EF class. C1 is going to class D. So if you see the pattern, there is no change in the pattern. That is, both states B and C are indistinguishable from each other and they can be collapsed in the same state. Similarly, for E0, E1, F0, F1, if we see the pattern, all the transitions go to the same state or the class EF. So EF also are indistinguishable and hence cannot be split further. They can be collapsed in a same state. So no need of splitting further. So by now, at the end of step 2, we have seen that no further split of the states can be done. So finally, we come across 4 classes: A, B, C, D and EF. By the end of this step, we came across A, B, C, D and EF, 4 classes representing 4 states: A, B, C, D and EF, where initial state is A and accepting state, here E and F are the accepting states. So in the minimized DFSM, E and F state is the accepting state. Coming to the delta transitions, A0 is going to state C. So A0 is going to state C. A1 is going to B. So A1 is going to B means BC state. Next, B0. B0 is going to state E. B0 is going to state E. B1 is going to state D. So B1 is going to state D. Coming to C. C0 is going to state F. So already we have a transition. C0 going to state F. C1 is going to D. So C1 is going to D. Then coming to D. D0 is going to E. D0 is going to E. D1 is going to F. So 1 is again in EF state. Coming to E and F, both are taking a self loop. So E and F both are taking a self loop for 0 and 1. So this is the minimized DFSM returned, which is equivalent to this FSM. This is how we go for minimizing the DFSM using min DFSM algorithm. Let us minimize the second FSM by using min DFSM algorithm. This FSM is over summation AB. So we'll see how the min DFSM operates at each step. So as we discussed in the previous example, initially we'll be having two classes. One class of accepting states, that is 2, 4. Another class of non-accepting states. Rest all states 1, 3, 5 and 6 will be in non-accepting states class. In step 1, we have to check if any class has more than one state, then is it possible to split that class further? So let us take up first class 2 and 4. 2a, 2b, 4a, 4b. 2a. 2a is going to state 3, which is in 1, 3, 5, 6 class. 2b is going to state 6, which is again in 1, 3, 5, 6 class. Similarly, on checking for 4a and 4b, we observe that both the states are in the similar pattern. It means 2a, 2b, 4a, 4b all are going to the same class 1, 3, 5, 6. That is 2 and 4 are indistinguishable states and they can be kept or collapsed in the same state. So no split required here. Same way we have to check for 1, 3, 5, 6 class. 1a is going to state 2, 2 is in class 2, 4. 1b is going to state 4, which is in class 2, 4. 3a is going to state 2, which is in class 2, 4. 3b is going to state 4 in class 2, 4. 5a is going to state 2, which is in class 2, 4. 5b is going to state 4, which is in class 2, 4. 6a and 6b are taking self loop to 6 itself, which is in class 1, 3, 5, 6. Now, if we see the pattern here, we'll get two different patterns. That is, 6a and 6b are going to the class 1, 3, 5, 6, which is different from the other classes. And whereas 1, 3 and 5 are in the same pattern. 1a, 1b, 3a, 3b and 5a, 5b are going to the same class 2, 4. That is, they are indistinguishable from each other and can be kept in the same state. So there are two different patterns split into class 1, 3, 5 and 6. Note that although class 6 has the same behavior as class 2, 4 after reading a single character, it cannot be combined with class 2, 4 because they do not share behavior after reading no characters. So by now the classes obtained are 2, 4, 1, 3, 5 and 6 at this step. At the end of this step, we came across 2, 4, 1, 3, 5 and 6, 3 classes. In the next step, step 2, we have to check whether 2, 4 and 1, 3, 5 classes can further be split or not. So let us see one by one. 2a is going to class 135, 2b is going to class 6, 4a is going to 6 and 4b is going to 135. And if you see, the patterns are totally different for 2 and 4 state. Hence, these two must be split into 2 and 4. Similarly for 135, so if you see the pattern here, 1, 3 and 5 all going to the same class 2 and 4. So it means they share the same pattern. They are indistinguishable from each other. So they can be collapsed in the same state. So no need to split them further. So by the end of step 2, we came across the classes 2, 4, 1, 3, 5 and 6. So in step 3, we are supposed to check whether 135 class can further be split into. In step 3, 1a, 1b, 3a, 3b, 5a, 5b all are going to state 2 and 4 respectively. On seeing the pattern, all the three belong to the same class, collapse in the same state, so no split required. So here splitting of the states stops. And finally, we are having 4 classes 2, 4, 1, 3, 5 and 6. So the minimized DFSM consists of 4 states 1, 3, 5, 2, 4 and 6, where initial state is 1. Coming to accepting state, in the DFSM accepting states are 2 and 4. So wherever we have 2 and 4 will be the accepting states of the minimized DFSM. Coming to the delta transitions, 1A is going to state 2, 1A is going to state 2, 1B is going to state 4, 1B is going to state 4. Next, 3A, 3A is going to state 2, already we have the transition. 3B is going to state 4, so that is also present. 5A, 5A is going to state 2, 5B is going to state 4. So 135 A is going to state 2 and B is going to state 4. Coming to state 2, 2A is going to state 3, which is in state 135. 2B, 2B, 2B is going to state 6. 2B is going to state 6. Next, coming to state 6, 6 is having a self loop for A and B transitions. Coming to state 4, 4a is going to state 6 and 4b is going to state 5, which is in 1 3 5. So this is the minimized DFSM obtained. If you see here, in the given DFSM we had 6 states, and in the minimized DFSM we have 4 states, and this minimized DFSM is equivalent to the given DFSM. So this is how we go for minimizing the DFSM using min-DFSM algorithm. This is example 3, for which you have to apply min-DFSM as I have done in for example 1 and 2, and minimize the DFSM. This is the minimized DFSM obtained for example 3. Similarly, I have given one more example, FSM 4, which is to be minimized. This is the minimized DFSM obtained for example 4. So you can solve these two examples 3 and 4. So if you have any doubts, you can ask me. You have my email ID with you. Thank you.